Hey everybody, Professor Fiore here, and in this video we are going to talk about superposition theorem using DC current sources, like so. So we already have a video that looks at superposition theorem with voltage sources, and I thought it would be a good idea just to take a quick look at what's happening with current sources, primarily because people often forget a very important characteristic. We very often start with voltage sources, and the statement that we make is for however many sources we have, we create that same number of equivalent circuits with only one source, and we replace all the other sources with their ideal internal resistance. For a voltage source, that means shorting it. And people get into the habit of seeing a source, shorting it, seeing a source, shorting it. But the ideal internal resistance of a current source is not a short, it's an open. And that will make a huge, huge difference. All right? So I just want to walk through this using a couple of current sources, and we'll find that the process is pretty much the same as what we saw in the voltage source version of that video. And if you haven't seen that video yet, I strongly recommend that you go and take a look at that one, because it gets into some of the details of the process, right? I really just want to focus on the current source part of it. As with voltage sources, or a circuit that's mixed, because you can use superposition if you have both voltage and current sources, you can use it to find node voltages, and you can also use it to find branch currents. We are going to look at both, all right? So I've set this circuit up with a pair of current sources, and a couple of resistors, and I've got two labeled voltages, right? I've got node voltage A and node voltage B. And I want to find out what those potentials are. So the way we would approach this using superposition is we would create two equivalent circuits. The first one with current source number 1, and then we would replace current source number 2 with its ideal internal resistance, which would be an open, right? Don't short it. And then we would do the same thing for the second equivalent circuit, looking at source number 2. We would open up current source number 1, and we would solve that. And we can solve those circuits, using any of the standard sort of series parallel techniques that we've used in the past. You could simplify them, use voltage divider rule, current divider rule, whatever floats your boat. All right? And then we find the items of interest. We can find the node voltage, we can find the current, let's say through R3, whatever it is. We find all the values of interest in each equivalent circuit, and then we simply sum the results to get the final value, remembering, of course, that we have to watch for polarities of voltages and directions of currents, right? Sometimes they add constructively, sometimes they partially cancel each other out, right? So we have to be aware of that. We have to be cognizant of that. So in this circuit, right, we have two sources, so we're going to get two equivalent circuits, and that's going to look like this. Here's our first equivalent circuit on the left, right? So here's that first current source we had, the 12 milliamp current source, and the other current source, the second source was out here, and we just open that up. So we just pull it right out, all right? And we can see we have just a current source and three resistors, a little series parallel combo over here. And then for the second equivalent circuit, we take that second current source, the 9 milliamp, and we do the same sort of thing where we open up the first current source. And we have a similar kind of situation, just a simple series parallel resistive element. So how do we want to go about, figuring out, let's say, the voltage across, node A or node B, okay? Looking at this, we would say, all right, a 3K and a 2K in series, that's 5K. And that creates a current divider with the 1K. Right? So I've got 12 milliamps coming into this node. There's a branch of 1K going down and another branch of 5K going off this way. So to find the current down through R4, right, we would take the opposite leg, which would be a total of 5K, over the total, in other words, 5/6 of 12 milliamps. Well, that would be 10 mils. So I'm going to have 10 mils down through here, and then the remainder 2 mils down through here. So either way you do that using Ohm's law, 10 mils times a K is going to get you 10 volts. 2 mils times 5K is going to get you 10 volts. So VA should be 10 volts. All right. And like I said, knowing we had a couple of mils going this way, right, 2 mils through the 3K, which is essentially in series with the 2K, knowing we have 2 mils there, we can use Ohm's law. 2 mils, 2K, that gets us 4 volts, and that's what VB is in this circuit. All right? Okay, moving over to the second equivalent, we take the 9 mils coming in, and again, we have a split. We have a 2K, and then a 3 in series with a 1. So that's a total of 4K. 2K versus 4K, that's a 2-to-1 current divider. So 2/3 of the current's going to go down through this 2K, and the other third is going down through this side. So 2/3 of the 9 mils is 6 mils. So 6 mils times the 2K, right? That'll give us 12 volts. And then the balance of 3, right? Yeah, 6, 9. So that would be 3 down through there. That would also give us 12 volts as expected. Then we could take that 12 volts, do a little divider, just like we did over here between the 3K and the 1K, right? So that's 1K over 4K, 1/4 of that potential, right? That was 12 volts. So 1/4 of that would be 3 volts. So now I take those pieces and we add them together, right? Take this voltage, add them together, take this voltage and this voltage, add them together, all right? So let's just real quick, like we'll just do a DC analysis here and see what we come up with, right? All right, so there's the 10 volts we were talking about. There's the 4, same thing over here, the 12 and the 3. So what we would expect when we're all done is that VA should be 10 plus 3 or 13, and VB should be 4 plus 12 or 16. Now we can also look at the current. So, to find currents, you can just use the node voltages in this case, do a differential voltage and Ohm's law, and you're good. So over here, I'd say, okay, I got 10 volts on this side, right? It's 10 volts from here to here. It's 4 volts from here to here. So it's 10 to 4. There must be a 6-volt drop sitting across our 6 here, the 3K. So you divide that out, and we get, as you can see on the probe, let me bring this over here so it's in the middle, 2 milliamps. So I've got 2 milliamps flowing left to right here. Now on this resistor, so we've got 12 volts down to 3. So the arrow, the reference arrow in TINA is pointing left to right, but you will notice that if you can squint, this actually shows up as -3 milliamps. Well, it's -3 in this direction, left to right, meaning it's positive right to left. All right, so 12 minus 3, that gives us 9 volts. 9 volts over 3K is 3 mils, so there's the 3 mils. So we're saying got 3 mils going this way, right? 3 mils going from node B to node A. And then over here, we said we have 2 mils going from node A to node B. So that partially cancels, right? That's 2 mils this way and 3 mils this way is only 1 mil this way. All right, so let us go back to our original circuit and see what we got. So we had 10 and 3, that's 13, and then 4 and 12 is 16 for the voltages. All right, so there we go, 13, 16, just what we expected. And then to check the current, right, there's -1 mil. Again, the reference direction is flowing this way, and we did expect 1 milliamp going that way, right? So there's 16 volts, 13 volts, so there must be 3 volts sitting across the 3K, which would give us 1 milliamp. Beautiful, okay? All right, so fairly straightforward process, but again, we have to emphasize this whole deal about replacement of sources. Don't think short. Think replace it with its ideal internal resistance. So for a voltage source, that's a short. For a current source, that's an open. Those are things you need to remember, right? Voltage source, ideal internal resistance is a short because the resistance limits how much output current you can get. In the case of a current source, it's the exact opposite, right? It's an open because any resistance in parallel with it would be limiting the voltage it could produce. So the ideal case, right, would be an unlimited case. So the paralleled resistance for a current source, the ideal internal resistance would be infinity. So you open this, right? Don't short it, open it, right? So that's, like I said, we had the source here and we had a source here. So we just open them, we pull them out. All right? Beautiful. Okay, so any questions, put them down in the comments, and I'll see you next time.